Good afternoon, physics friends. It's Miss Clover here just to try to help you out a little bit with some of the book problems. I'm starting by looking at chapter 30, problem 82, and this one has American physicist Robert Millikan, who won the Nobel Prize, working on the photoelectric effect. And he, using lithium, he found a max Ke of 0.550 electron volts when electrons were ejected with 433.9 nanometer light. And for light of 253.5 nanometer, he observed a max Ke of 2.57 electron volts. Those wavelengths. It asks, using these results, predict the work function for lithium, the predicted value of Planck's constant, and so on. So what I kind of have two different sets of data, so I can set up two equations with two unknowns using Ke max equals HF minus phi. So 0.55 electron volts, converting 1.6 times 10 to the minus 19 joules per electron volt will equal Hc over lambda minus phi, the work function. This is my first equation, and my second equation would be 2.57 electron volts convert into joules equals Hc over lambda minus phi. So we have two equations, two unknowns. We can go ahead and either use substitution, solving for one, or I think I just straight up subtracted them. So took this whole equation minus this whole equation, and I was able to solve for H equal to 1.94 times 10 to the minus 34 joule seconds, and I was able to get phi to be 4.64 times 10 to the minus 20 joules, or 0.29 electron volts. And then for part C of this, so that's kind of A and B, what is the maximum kinetic energy you predict? So what would Ke max be using light with wavelength of 365 nanometers? So if I do H is 6.626 times 10 to the minus 34, 3 times 10 to the 8th, divided by a wavelength of 365 times 10 to the minus 9 meters, minus phi, just 4.64 times 10 to the minus 20 joules. From that, I would get a max Ke here. Drum roll, of 4.98 times 10 to the minus 19 joules, or 3.11 electron volts of energy. Let's see, moving on. guess if we look at chapter 31, number 58, and in chapter 31, number 58, you had to do the energy difference, and I got the difference between level 1 and level 2 to be 10.2 electron volts, or that would be 1.632 times 10 to the minus 18 joules. Once you had that energy, we could set it equal to the internal energies, and it would be 3/2 KB, the Boltzmann's constant, times T, the temperature. And I got T, the temperature, to be 78,840 kelvins. Very hot, hot, hot. And let's see, in the atomic packet, we could look at check out question 2 to 3 from this diagram. How much energy in electron volts must be absorbed by an electron in the first energy level to jump to the third? Well, the difference from the first to the third would be a difference of 13.6 minus 1.5, or 12.1 electron volts. Determine the frequency and wavelength of the light emitted, as in the third energy level, returns to the ground state. So we know it's got an energy of 12.1 electron volts, and that would be equal to 1.936 times 10 to the minus 18 joules. So if we set that equal to Hc over lambda, or Hf, I was able to find the wavelength would be 1.03 times 10 to the minus 7 meters, and the frequency would be 2.91 times 10 to the 15th hertz. Other ones we could look at. For hydrogen, remember that the energy levels would be negative 13.6 electron volts divided by n squared. So if we wanted 6th or 8th, it would be negative 13.6 divided by 6 squared, or negative 13.6 divided by 8 squared. And so I got, for this, 0.370 electron volts, and if you did 13.6 divided by 8 squared, you got 0.213 electron volts. The difference in energy, it goes into the energy of the photon, so it would be 1.165 electron volts, or 2.64 times 10 to the minus 20 joules. To then find the frequency, do E equals HF. To find the wavelength, you can use E equals Hc over lambda, plugging in this energy, and H 6.626 times 10 to the minus 34 times F. Okay. Is it in the electromagnetic spectrum? Remember, for that you got to name drop and say 400 to 700 nanometers, and the answer was no. For each of these, it was just outside.